of where we've been in this conversation before we go on. Recall that we first started out this conversation with enthalpy in the context of organic chemistry. And the units we used for that were not units, but the symbol we used for that was H, right? And we related that to bond energies mostly, right? And the change in enthalpy of a reaction we call delta H, and that's going to be super useful to us. So enthalpy is the first term. The second term is entropy, and we described that as the degree of disorder or the number of states a system has access to. We talked about flipping coins. We talked about gases going to bigger volumes. The symbols we used for that were S and delta S, where delta S is the change in entropy of a system, right? So if the change in entropy of a system, if a system gets more organized, it gets less disordered, then the delta S is going to be negative. If it gets more disordered, it's positive, okay? And we take both of those terms and we relate them we wrap them all up in one term called free energy. Free energy tells us if a system's going to go, if a reaction is spontaneous or not. So the symbol we use for that is G, because we're going to be using specifically Gibbs free energy, right? So the change in free energy of a system is delta G, and we said delta G is related to enthalpy and entropy, as delta G is equal to the change in enthalpy of a system minus T delta S, right? And if this is negative, if delta G is less than 0, then we say a reaction is spontaneous. Okay? And at the end of that conversation, we said that no, it was the next one. The next thing we talked about was equilibria, and in equilibria we talked about free energy again, and in equilibria we said we're going to describe an equilibrium with KEQ, as in the products over reactants, right? And we said delta G, right, free energy of a system now has to do with the ratio of products to reactants. So if the ratio of products to reactants is such and such, then the delta G is going to be so and so, right? And this is related to temperature and R. All right, now we emphasized at the end of this conversation that this has nothing to do with rates. We used an example of diamond turning to graphite, which is a spontaneous reaction. That is, delta G is less than 0, it's negative, but it's super, super slow. So sometimes we'll find that even though a reaction is spontaneous, we're not going to, in our lifetimes, see it happen because it's so slow, right? So that introduces another concept called kinetics. That is rates of reaction. Okay, we're going to talk about kinetics now, but let me give you a quick sort of overview where we're going with this. We are going to consider these two sometimes in contrast. Sometimes they go together and sometimes they don't. And we're going to use graphs, I think, to help you appreciate that in more detail. So first of all, let's define kinetics. Kinetics is mostly going to be in the context of a rate, and rates are a distance per time, as always, right? We've been doing this since we were studying for the SAT, since we did I think, first year algebra in high school. That is the number per time, right? Number per time, distance per time. In this case, kinetics is going to be the number of molecular collisions, frankly, successful molecular collisions per time. And that's what we're going to be talking about when we talk about rate. Now, there are 5 factors that affect rate. That is how many reactants we have to collide, right? What the activation energy is for a system. So are the collisions going to be successful or not? We're going to go over these one at a time, okay? The temperature, that is how fast they collide. The geometry, that is, can they get into the right orientation to collide successfully, right? And then also presence of a catalyst. And so we'll deal with each of these in turn. So again, kinetics is mostly going to be concerned with the rate of a reaction, where rate is defined as the collisions per time, and these are factors that affect it. So let's get a little deeper. Now, when we talk about rates, we're going to quantify this by using something called a rate law. I remember as an 18 or 19-year-old student seeing rate law, and that sounds like rate law is going to be, at Parber westward, Fort to Causeway is 2 at Parber and whatever, right? So some long sentence. But the rate law in chemistry is always going to be given like this. The rate law is going to be rate is equal to some rate constant times the concentration of the starting materials. This is the rate law right there. Boom. Okay? This is a very general rate law because I haven't said what the K is and I haven't said what the reactants are, right? Now the rate depends on the rate constant. You can see as K goes up, rate's going to go up, right? That's linear. And it depends on the concentration of the reactants. Now, the degree to which the change in reactant, the degree to which the rate, the change in reactant will affect the rate is known as the order. The degree to which the amount of the reactant will affect the rate is called the order. I'm going to give more on this next slide for that. Watch this. Now, the order of a reaction is represented by x and y. Okay, well, this is very much like a polynomial we did in algebra. Okay, so the rate, same, you see a rate law here. There's my rate law. There's my rate constant. Now, if x is 1, then we would say this is first order with respect to A. If x is 2, we would say it's second order with respect to A. If it's 3, we would say it's third order with respect to A. Okay? So, of course, we would say the same with y, and then we would say overall order, okay? Look at this. Now, can you see that there's only, if we're counting the exponents for this, b is here, I guess, but it's 0, right? Can you see that this, if I add up all my exponents, I have 1, right? 1 plus 0 is 1. So this is first order. That means that there's only one dimension here, okay? A second order is if I have a 1 and a 1 here, right? Third order is if one of these is 2. Third order overall. This reaction is second order with respect to A and third order overall. Okay? So in this, let's give a little summary down here. If A is doubled, can you see that? If A goes from, say, 1 molar to 2 molar, the rate's going to be doubled. Right? So if A is doubled in a first order reaction, the rate is going to be doubled. If A is doubled here, since it's first order with respect to A, if A is doubled, it goes from 1 to 2, then the rate is going to be doubled. Over here now, if A is, if this is the rate law, we're talking about a reaction that's second order in A, then when A is doubled, right? So the concentration of A is doubled. You can see that the rate is going to be quadrupled. Okay, and that's what that's about. So get used to looking at that. Of course, we'll have plenty of practice with it, but we're going to ask some simple questions here with respect to it. So we're going to derive a tremendous amount of value from understanding rate law. So I know we got this in Gen Chem, but we need it now, and we want to take a few minutes to review it. Now, the activation energy is the energy barrier between the reactants and products. That is, the activation energy is the height of that peak. That's the height, okay? So the higher this is, the slower it is. We're going to get into that next couple slides. So that says nothing. Can you see that says nothing about the difference between these here, right? If this is potential energy, free energy, this is going to be delta G. That difference is delta G, okay? That tells us about equilibrium. But the rate has to do with the activation energy. Okay, the activation energy is the minimum amount of energy required for molecular collision to be successful. All right, now, as the activation energy increases, the number of molecules possessing enough energy to react decreases because these, you may recall, depending on your treatment of Gen Chem 2, that the amount of energy particles have is not uniform, right? It follows a Boltzmann distribution such that which is what we have here. This is a Boltzmann distribution. The number of molecules that have a particular amount of energy, right? It's not exactly normal because you can't have less than 0 energy, right? So a Boltzmann distribution says, well, the number of molecules, it increases. So we've got a lot of molecules that have this much energy. That's the maximum number, right? Most molecules, or the greatest number of molecules in this sample have this much energy. But as it gets higher, fewer and fewer molecules have enough energy. So activation energy is the minimum amount of energy that a particle's got to have that's got a particle has to have in order to get over the hump, right? And as that activation energy gets higher, then it's a fewer number of particles that actually have that amount. That was a very clumsy explanation, but you can imagine the higher a hill is, the harder it is to get over it. Let me say that again. The higher a hill is, the harder it is to get over it, and the fewer particles that can get over it, okay? Now, the lower the activation energy, the faster the rate, just like you might expect. So, if this is delta G, right? If that's delta G, and this has to do with equilibria, the height here is activation energy, and this has to do with rate and the kinetics. These two are not the same thing. You can imagine you can have, this is a good example, where these two have exactly the same delta G. Can you see that? These two graphs are put next to each other. They have exactly the same delta G. But this has a higher hill to get over. The activation energy is higher, and so therefore it's going to be slower. Yes, it's that simple. Okay, now temperature, it affects the rate because as temperature goes up, we have a larger number of particles that have a higher energy, right? So a higher number of particles, can you see, as the temperature goes up, this Boltzmann distribution is going to get skewed to the right, and there are going to be more particles that have enough energy, and that will increase the number of particles that have enough to get over the activation energy, where this here, right, that's arbitrarily set as just as an example. This isn't, suppose that's an activation energy. And as this Boltzmann distribution shifts to the right, because the temperature goes up, you can see we're going to have a lot more particles that have the energy to get over the hump. All right. So steric considerations also need to be taken into consideration. Steric hindrance, that is, things that get in the way, affect the rate of reaction, because when two molecules collide, if they can't get to each other, if the electrons can't get to the right spot, then you can't make the new bond. It's that simple. Okay, so when molecules collide, they have to be in the correct orientation for bonds to be made or broken. And if the reactive conformation of a compound is high energy, it's going to spend less time in that conformation. So the probability of collision resulting in a reaction is slow. So we're going to get into this in a great deal in the upcoming conversations, but it's important for you to appreciate that two molecules, if they're going to collide successfully, they've got to make the successful collision in the right geometry. Okay, catalysts are important because you remember this from Gen Chem 2. Catalysts oftentimes decrease the activation energy, and if you've got a catalyst which is going to cut off that hill, then obviously there's going to be a lot more particles that have enough energy to get through the hill or over the hill, right? And then finally, recall that kinetics and thermodynamics are completely different concepts. I've said that a couple times here in this conversation, but let me emphasize it again. That kinetics has to do with how high this hill is, and thermodynamics has to do with the difference in energy between the reactants and the products. Okay, let's move on.